Box 6.4 Language and Numerical Cognition. Humans share with other animals an ability to precisely represent small numbers and approximately represent large numbers, but human adults are also able to manipulate exact numbers in ways that go beyond the abilities of animals. For example, we can quickly determine how many items will remain after 3 are removed from 6, likely by using our counting skills. In Box 6.2, the relationship between the approximate number system and formal math skills was discussed, but here a different relationship will be considered, the relationship between language and number cognition. Specifically, there has been a resurgence of interest regarding the extent to which language might affect or even create our number concepts. Western language systems allow for infinite enumeration, but the languages of some other cultures have a very narrow set of number words, e.g. 1, 2, many. These languages offer a unique opportunity to examine the relationship between number cognition and language. For example, the Munduruku tribe of the Amazon in Brazil uses count words for 1, 2, and 3 consistently, but not for larger quantities. When asked how many items are in an array of 5 or more, they may reply with words that indicate some or many. Another tribe, the Paraha, do not even use words for 1 and 2 consistently. Number discrimination and simple operations have been examined in these groups. For example, Pika et al. 2004 found that Munduruku participants were able to discriminate and add large approximate numbers, up to 80 dots, in a manner similar to a French-speaking group. Further, both groups' performance on the estimation tasks varied according to Weber's law. The judgments were more accurate for larger ratio discrepancies. However, in exact arithmetic tasks with numbers larger than 4 or 5, e.g. 8 minus 5, the Munduruku participants had lower performance than the French participants. Similarly, the Paraha had difficulty representing medium-sized sets of 4 or 5. This cross-cultural work further supports the claim that there is an approximate number system that is shared across humans and many animal species that does not rely on language, yet it also suggests that for humans, number language allows for precise arithmetic beyond small numbers. Which came first, though, the language or the concept of exact quantity? One particularly controversial proposal is that number language itself actually creates the precise number concept. An alternative proposal is that number language allows for a precise representation of quantities by perhaps reducing memory demands and enabling more efficient coding, but that the initial development of a number concept is independent of language. Both proposals thus implicate language as a factor in connecting the abilities we share with animals to our unique precise number skills. Determining the exact role of language, however, is a challenge for developmental psychologists and linguists, but in concert with comparative work with animals, will help complete our understanding of numerical cognition. Chapter Summary. 2 primary types of timing have been characterized, one for cyclical activity that occurs during a 24-hour period, periodic timing, and one timing system for much shorter durations on the order of seconds or minutes, interval timing. The internal circadian rhythm for periodic timing is typically discussed in terms of physiology, not cognition. However, animals may learn about events that occur at certain times of day, linking the event to the internal clock. Laboratory experiments examining interval timing, including those using the peak procedure, have found that for animals and humans the ability to discriminate among short durations depends on Weber's law. Greater variability in responses occurs as the to-be-timed durations get longer. Different models of interval timing exist, 3 types of which do well to describe the current data. Although there is no consensus regarding which model is best, each has inspired new research and paradigms. Discriminations between 2 durations and discriminating between 2 arrays of objects share a common feature. Both are instances of discriminating magnitude. Indeed, many have hypothesized that timing and numerical processing originate from a similar, if not common, representational system. For human infants and animals, when discriminating approximate numerosities, the ratio difference is important. 1 to 2 ratios are discriminable, but 2 to 3 ratios prove difficult. In fact, the ratio difference appears to be more relevant than the absolute number difference, a feature of Weber's law. Cognitive models of the approximate number system posit that a real-world value is represented in the mind as an analog of that value. This analog magnitude representation is a noisy representation of the set of items, yet it is proportional to the number of items being represented. Based on the set size signature found across various species in tasks assessing small number discrimination, many researchers have proposed that there are at least two distinct mechanisms for processing number: a precise small number system and the approximate number system. One proposed mechanism that likely underlies small number discrimination in some situations is an object tracking system. Some have proposed that a true concept of number should include an understanding that number is an ordered system and the ability to perform simple addition and subtraction. Each of these numerical operations has been observed across a wide range of species. Though the cognitive and neural mechanisms supporting a concept of number are still under investigation, the comparative study of numerical processing, as well as timing, has led to great advances in our knowledge.